In the silent dark between galaxies, something invisible is bending starlight sideways. The James Webb Space Telescope just mapped it, and the map is wrong. Dark matter is sitting where no galaxy lives. Entire clusters are missing their halos. A dwarf galaxy glows with almost none at all. You will see a filament stretching through empty space, a halo tilted off its galaxy, and a collision where the invisible stuff raced ahead of the stars. If cosmic mysteries pull you in, hit that like and subscribe button so more of these reach you. Sit back, dim the lights. We begin. The image came through at 3 in the morning, and the room went quiet. A small team at the Space Telescope Science Institute had been waiting months for this data. The James Webb Space Telescope had aimed its golden mirrors at a single patch of sky, a cluster of galaxies sitting roughly 4 billion light-years away. The goal was simple on paper. Map the gravity, map the mass, find the dark matter. Dark matter is the invisible stuff that holds galaxies together. You cannot see it, you cannot touch it. Light passes through it, like it is not there. Yet it makes up about 85% of all the matter in the universe. Every star you have ever seen is floating inside a vast ocean of this unseen material. Without it, galaxies would fly apart in minutes. Scientists had mapped dark matter before. Older telescopes like Hubble gave blurry outlines, soft glows of mass surrounding galaxy clusters. Those maps looked tidy. Dark matter sat where the galaxies sat. It wrapped around them like a coat around a body. Everything lined up. Everything made sense. Then Webb turned on its infrared eyes. Webb sees in a way Hubble cannot. It captures light stretched across billions of years. Light so faint that older instruments missed it entirely. When Webb stares at a galaxy cluster, it sees hundreds of background galaxies behind it, each one warped and smeared by the cluster's gravity. Those warps are clues. They trace the shape of the invisible mass. The team fed the data into a program that turns warped starlight into a gravity map. The screen blinked. The map loaded. Someone in the room said, "That can't be right," because the dark matter was not where the galaxies were. Chunks of it were drifting in the empty space between them. A thick ridge of invisible mass ran through a region where Webb saw nothing at all. Parts of the cluster where hundreds of galaxies glowed brightly had almost no dark matter above them. The shape was wrong, the distribution was wrong. It looked like someone had taken the expected picture, torn it into pieces, and thrown the pieces across the sky. They ran the numbers again. They checked the calibration. They called in 2 other teams to repeat the work independently. Every result came back the same. Dark matter was sitting in the wrong places. This was the first of many such maps. Webb would go on to image cluster after cluster, each with its own strange signature. Some had halos twisted sideways. Some had invisible bridges reaching into empty voids. One cluster had a dark matter clump with no galaxy inside it at all, a ghost with no body. For decades, physicists had built a confident story about how the universe was put together. Galaxies formed inside halos of cold, dark matter. The halos grew slowly, pulled stars inward, and anchored everything in place. It was elegant. It was tested. It was taught in every university textbook. Webb just put cracks in the foundation. What those cracks mean is something scientists are still working out. Some think they point to new physics. Some think dark matter itself is not one thing, but many. A few quietly wonder if dark matter, as we imagined it, exists at all. The first map was only the beginning. The next one would be stranger. For almost a century, scientists were sure they knew where dark matter lived. The story started in the 1930s, when a Swiss astronomer named Fritz Zwicky pointed his telescope at a distant cluster of galaxies. He watched the galaxies whirl around each other at tremendous speeds. He did the math. The galaxies were moving too fast. The visible matter in the cluster could not hold them together. They should have been flung into deep space like sparks from a grinder. Something invisible was pulling them in, something heavy, something dark. Zwicky called it Dunkel Materie, German for dark matter. The name stuck. The idea did not, at first. Most astronomers ignored him for 40 years. Then, in the 1970s, an American astronomer named Vera Rubin studied how stars move inside individual galaxies. She expected stars at the edge of a galaxy to move slower than stars near the center, the way outer planets in our solar system orbit slower than inner ones. That is how gravity works when the mass is bunched in the middle. Her measurements showed the opposite. Stars at the outer edges were moving just as fast as stars near the middle. Entire galaxies were spinning like solid dinner plates instead of like whirlpools. The only way that made sense was if a massive, invisible halo surrounded each galaxy, holding the outer stars in place with its gravity. Rubin had found the shape of dark matter. It was a giant sphere, a puffy ball of invisible mass, wrapping around every galaxy like a thick winter coat. This idea became the foundation of modern cosmology. Galaxies sat at the center. Dark matter halos enveloped them. Stars, gas, and dust all lived inside these invisible cocoons. Smaller halos orbited bigger ones. Galaxy clusters sat inside gigantic superhalos, stretching millions of light years across. The model had a name: cold dark matter. Cold because the particles were assumed to move slowly, dark because they gave off no light, and they were thought to be everywhere that galaxies were. Computer simulations backed this up beautifully. Scientists plugged cold dark matter into their virtual universes and watched galaxies grow. The simulations produced structures that looked strikingly like the real cosmos. Filaments, clusters, voids, it all matched. Every major discovery for decades fit the picture. The cosmic microwave background, the faint afterglow of the Big Bang, carried patterns that only made sense if cold, dark matter filled the early universe. Gravitational lensing surveys, where light bends around massive objects, showed dark matter halos, tracing galaxy positions almost perfectly. Dark matter hugged galaxies. That was the rule. Where you found light, you found dark. Where you found galaxies, you found the halo. It was as dependable as finding water under a lake. Textbooks drew the same diagrams for 40 years. A bright galaxy at the center, a fuzzy blue sphere of dark matter around it, an arrow pointing to the sphere. The label, simple and confident: dark matter halo. That image was in every astronomy class, every documentary, every research paper. It was the settled picture. Then Webb launched. Webb saw more. Webb saw sharper. And Webb started finding halos that did not sit where they were supposed to sit. One of the first strange cases was a cluster where the dark matter had apparently drifted, far from the galaxies, into empty space. The cluster had a boring catalog name, a string of letters and numbers that meant nothing to anyone outside a research paper. Call it the drifting cluster. When Webb first imaged it, the picture looked normal. Hundreds of yellow and red galaxies packed into a tight region of sky, glowing softly in the infrared, a few bright stars in the foreground, the usual scatter of smaller galaxies in the background. Nothing unusual to the eye. The strangeness showed up only when the team built the mass map. To make a mass map, you do not look at the galaxies themselves. You look at what is behind them. Light from faraway galaxies travels for billions of years before reaching Webb. On its way, that light passes through the gravitational field of clusters like this one. Gravity bends light. A massive object acts like a giant lens, warping the shapes of galaxies sitting behind it. By measuring how those background galaxies are distorted, you can calculate how much mass sits in front of them and where exactly that mass is placed. The galaxies become little arrows, all pointing toward invisible gravity wells. When the team at Webb ran this calculation, the result looked broken. There were gravity wells, plenty of them, but the deepest wells were not centered on the galaxies. One giant pocket of mass sat off to one side of the cluster, in a region with almost no visible galaxies at all. Another massive lump was floating in what looked like empty space between two galaxy groups. The cluster's brightest concentration of galaxies, meanwhile, had a smaller dark matter signal than expected. The dark matter was somewhere else. Picture an ordinary scene, a crowd of people standing in a park. You expect each person to cast a shadow near their own feet. That is how light works. That is how mass should work too. Each galaxy should have its own invisible halo sitting right underneath it. Now imagine walking into the park and seeing shadows drifting off to the side. One shadow 100 feet from its person. Another shadow with no person at all. a whole knot of shadows clustered where no one is standing. That is what the Webb map looked like. The shadows had wandered. The team checked the usual suspects: a foreground galaxy they had missed, a calibration error in the infrared detectors, background noise from cosmic rays. Each possibility was ruled out, one by one. Other groups repeated the lensing analysis using independent methods. The drifting mass stayed exactly where Webb said it was. Estimates put one of the rogue dark matter clumps at roughly 200,000 light-years away from the nearest bright galaxy. 200,000. That is about twice the width of our entire Milky Way. Picture a silent mountain of invisible gravity, heavier than billions of suns, sitting alone in the middle of nowhere. A few possible explanations started making the rounds. Maybe the cluster had recently collided with another one, and the collision had stripped the dark matter away from some of the galaxies, the way a truck crash can fling cargo miles from the wreckage. Maybe a galaxy had been torn apart long ago, leaving only its invisible skeleton behind. Maybe dark matter itself does not always travel with visible matter the way the textbooks said. Whatever the cause, the rule had been broken. Mass and light could come apart. To understand how Webb even sees this invisible stuff, you have to understand its sharpest trick, a technique that turns gravity itself into a lens. You cannot photograph dark matter. It emits no light. It absorbs no light. It does not glow at any wavelength, from radio waves to gamma rays. Every telescope ever built, including Webb, is blind to it directly. Yet Webb can map it in stunning detail. The trick has a name: gravitational lensing. The idea came from Albert Einstein more than 100 years ago. Einstein showed that gravity is not really a force pulling things together. Gravity is a warp in the fabric of space itself. Heavy objects bend space around them the way a bowling ball bends a trampoline. Anything passing by, including light, has to follow those bent paths. When light from a distant galaxy travels past a massive object, like a cluster of galaxies, its path curves. A straight beam becomes a smeared arc. A round galaxy in the distance appears stretched into a banana shape. Sometimes the light splits, and you see the same galaxy in 2 or 3 different spots on the sky. Sometimes it forms a perfect ring, a glowing circle wrapped around the foreground mass. These are called Einstein rings. This means every massive object is a lens. The universe itself is full of giant natural telescopes, and Webb can see through them. Here is the brilliant part. The amount of bending tells you how much mass is there, and the direction of the bending tells you where the mass is. You do not need to see the mass at all. The warped background does the work for you. Hubble could do this, but only roughly. Hubble sees invisible light. Many distant galaxies are so red-shifted, so dimmed by cosmic expansion, that their light barely registers on Hubble's sensors. It was like trying to read a book in candlelight. Webb reads in infrared. Infrared light cuts through cosmic dust and carries the signatures of galaxies from the universe's earliest era. Galaxies that looked like faint smudges to Hubble appear as sharp little ovals to Webb. Where Hubble might catch 20 warped background galaxies behind a cluster, Webb catches hundreds, sometimes thousands. Every one of those warped galaxies is a data point. Each one tells you, there is mass here, bending me this way, with this much strength. When you stack all those measurements together, a picture emerges, a gravity portrait, a dark matter map. Imagine standing by a swimming pool at night. You cannot see the water clearly in the dark, but you can see the shimmering lights of houses on the far shore, reflected and bent by the pool's surface. By studying the shimmer, you could figure out the shape of the pool, the depth, even the ripples moving across it. Webb does that with space. The galaxies behind a cluster shimmer. The mass in front reveals itself through their distortions. Early maps showed soft, smooth halos around clusters. They looked the way theory predicted. With Webb's sharper lensing power, the maps got finer. Lumps appeared, streaks, offsets, little rogue concentrations. For the first time, scientists could see not only where dark matter was, but where it was not. They could watch it sit in one spot while galaxies sat in another. They could spot filaments too thin for Hubble to have detected. And one of the first things Webb's lensing power revealed, in a single famous cluster, was something already suspected but never seen this clearly. A bullet of dark matter that had run ahead of its own galaxies. About 3.5 billion light-years from Earth, two galaxy clusters once collided head-on. This was the kind of collision the universe reserves for its most violent demonstrations. Each cluster contained hundreds of galaxies, trillions of stars, and vast reservoirs of hot gas. They slammed into each other at roughly 10 million miles per hour. The wreckage is still spreading. Astronomers call the aftermath the bullet cluster. It is one of the most photographed, most argued over objects in the sky, and it is the single clearest proof that dark matter is real. Here is why. When galaxy clusters collide, different parts of them behave differently. The galaxies themselves are mostly empty space. They pass through each other like two swarms of bees flying through one another. They barely interact. They just keep going. The gas is a different story. Clusters contain enormous clouds of hot gas between their galaxies, millions of degrees, glowing in X-rays. When two clusters slam together, the gas clouds crash and drag. They slow down, they pile up in the middle, they form a giant shockwave shaped like a bullet, which is where the name comes from. So after a collision, you expect this. The galaxies keep flying forward on either side. The gas lags behind, stuck in the middle, and the mass should be mixed up accordingly, heavy with gas in the center, lighter at the edges. The first strange result came years ago, from older instruments. When astronomers mapped the bullet cluster's mass using gravitational lensing, the mass did not sit with the gas. Most of the mass was on the sides, traveling with the galaxies. The gas, even though it was much heavier than the stars, was not where the gravity was. The conclusion was stunning. Most of the mass in the cluster was invisible. It had passed right through the collision without slowing down, like a ghost walking through a wall. It had not stuck to the gas. It had stuck to the galaxies. Or rather, it had flown alongside them, only loosely connected to anything visible. That was dark matter. Proof it was real. Proof it barely interacts with normal matter or with itself. Proof it was not just a mistake in our theory of gravity. Webb has now looked at the bullet cluster with its own eyes, and the new images have made the evidence even sharper. With Webb's infrared vision, astronomers can count far more background galaxies warped by the cluster's gravity. The dark matter map, redrawn, is higher resolution than anything before. You can see the two dark matter bullets clearly, racing ahead on either side of the gas. You can see the hot gas glowing behind them, a bright pink blob in the middle, stuck and slow. You can see, frozen in time, a picture of two different kinds of matter separating during a cosmic car crash. It is as if the universe set up the perfect experiment and left it out for us to find. But the bullet cluster is more than just evidence. It is a warning. It shows that dark matter can come apart from normal matter. It can drift, it can lead, it can lag. Under the right conditions, it goes its own way. Webb has been finding those conditions all over the sky. And in one case, the dark matter did not just drift, it stretched into something nobody expected. Between galaxies, space looks empty, deep, black, endless. You would think there is nothing out there. There is. A web. Astronomers have long suspected that the universe is structured like a vast cosmic cobweb. Galaxies are the bright droplets on the strands. Between them stretch long, thin filaments of gas and dark matter, threading through the dark. These filaments link galaxy clusters the way bridges link cities. They form the skeleton of everything. Older telescopes could hint at the web. Hubble caught fuzzy outlines of some filaments near large clusters. Radio telescopes detected the faint warmth of hot gas flowing along certain strands. But nobody had ever clearly imaged a pure dark matter filament floating alone in the void, until Webb. One survey targeted a patch of sky between two massive galaxy clusters separated by about 30 million light-years. The region between them looked empty in every previous image. No bright galaxies, no obvious gas, just black. Webb's lensing analysis found something in that black. Running straight through the empty zone, like a rope pulled taut, was a long concentration of mass. It had no bright stars along it. It had no detectable galaxies. It gave off no light. but it warped the background galaxies behind it in a clean, continuous line. The gravity was bending starlight in a stripe across the sky, a filament of pure dark matter, tens of millions of light-years long, silent, invisible, heavy. To understand the scale, imagine walking across a frozen lake at midnight. You see two distant villages on opposite shores, their lights twinkling far away. The lake between them looks empty and dark. Then you put on special glasses. Through the glasses, you see a giant, glowing cable running under the ice, linking the villages from below, thicker than a skyscraper, stretching for miles. It was always there. You just could not see it. That is what the Webb filament felt like to the astronomers who found it. The discovery mattered for a few reasons. First, it confirmed that dark matter really does form cosmic bridges between clusters. The theorists were right about the Webb. Second, it showed that some parts of those bridges are almost completely devoid of normal matter. No stars formed there, no gas collected there. The dark matter is in some places without the light. Third, and most unsettling, the filament's shape did not quite match the predictions. In most simulations, a filament connecting two big clusters should have little knots along it, spots where gas and dark matter bunched up enough to form small galaxies or groups. The Webb filament had fewer of those knots than expected. It was smoother, thinner in places, lumpier in others. It looked like a river, but a river with a strange, uneven flow. One theorist described it as a strand pulled out of the textbook and then roughed up by hand. Questions started stacking up. Why are some filaments emptier than predicted? Why do some have odd lumps? Does dark matter flow through these strands at different speeds in different places? Could the filaments themselves be evidence of new physics, something the old models never captured? Webb found a dark skeleton in the empty sky. It was both a confirmation and a warning. The bones of the universe are real. They are also a little stranger than we drew them. The next surprise went in the opposite direction. A galaxy with almost no dark matter at all. Every galaxy should have a thick halo of dark matter. That was the rule. It held up for almost 50 years. Every galaxy Rubin studied, every cluster Hubble imaged, every simulation run on every supercomputer produced the same answer. Dark matter and galaxies go together. You cannot form one without the other. A galaxy without dark matter would be like a ship without a hull. It should not exist. It should not hold together. Then Webb looked at a small, faint smudge about 65 million light-years away. The galaxy had been catalogued before. It was an unremarkable-looking dwarf, pale and diffuse, the kind of object astronomers call an ultra-diffuse galaxy. Most of these little galaxies are thought to be stuffed with dark matter, sometimes 100 times more of it than visible stars. They are fragile structures, often held together almost entirely by their invisible halos. This one was different. Even older Hubble images had hinted that something was off. The stars inside it moved slowly, far too slowly, for a galaxy with a normal dark matter halo. When you see stars moving slowly, it means the gravity pulling on them is weak, which means there is not much mass around them. Webb confirmed it. With its sharper resolution, astronomers could pick out individual stars, measure their velocities precisely, and build a real three-dimensional map of the galaxy's interior. The result was bizarre. This galaxy had almost no dark matter at all. The stars and gas alone were enough to explain its structure. The invisible halo, the giant cocoon, the thing every galaxy was supposed to have, simply was not there. According to the standard model of cosmology, this should be impossible. Galaxies form inside dark matter halos. The halo comes first. Gas falls into it. Stars ignite. The galaxy grows. Take the halo away, and nothing forms. Take the halo away after the galaxy forms, and the galaxy flies apart in a cosmic blink. Yet here it sat, intact, serene, ordinary looking from the outside, naked on the inside. The response in the astronomy community was sharp. Some teams rushed to double-check the measurements, hunting for errors. Others began writing new papers, proposing exotic origins. Maybe this galaxy had been stripped of its dark matter by a violent near-miss with a larger galaxy, its halo torn off like a cloak. Maybe it had formed from gas ejected during a collision, spawned directly from the debris rather than inside a halo. Maybe it was not one galaxy at all, but a chance alignment of several smaller ones. None of the explanations were fully satisfying. Ripping a halo off a galaxy is extremely hard to do. Forming a stable galaxy without one is even harder, and Webb has already found more than one case like this. Several other dark matter-like galaxies have now been identified, scattered across the nearby universe like anomalies waiting to be explained. If even a handful of galaxies can exist without dark matter, something in the big story is wrong. Either our models of galaxy formation are incomplete, or dark matter behaves in ways the equations have not captured, or the rare cases are hiding a deeper rule nobody has written down yet. The universe, it turns out, can build galaxies in more than one way, and if it can build them without dark matter, the next question is inevitable. Why do other galaxies have so much more of it than they should? For every galaxy Webb finds with missing dark matter, there is another one drowning in it. These are the ultra-heavy dwarfs, tiny galaxies, some no bigger across than a few thousand light-years, each one weighing far more than their starlight suggests. If you tried to account for their mass using only the stars, the gas, and the dust, you would fall short by factors of 10, 20, even 100. The rest of the mass is invisible. One nearby example, known as Dragonfly 44, was already famous before Webb. Earlier observations suggested it might be almost entirely dark matter, with only a thin sprinkle of stars floating inside a massive halo. Astronomers called it a failed Milky Way, a galaxy that should have grown as big as our own, but somehow never lit up properly. Webb has now imaged several cousins of Dragonfly 44. Some look even more extreme. The problem is not that these galaxies have dark matter. All galaxies were supposed to. The problem is the ratio. The amount is wildly out of proportion to their visible size. It is as if someone built a small cottage on top of a foundation meant to hold a skyscraper. To picture the imbalance, imagine two houses on a street. One is a mansion, 10 bedrooms wide, with a garden and a pool. The other is a tiny bungalow next door. You would expect the mansion to have a larger basement, a bigger foundation, more plumbing underneath it. Now imagine you peek underground. The mansion has a small, simple basement. The bungalow has a cavern the size of a stadium buried under it. That is roughly what these dark matter-heavy dwarf galaxies look like. Webb has mapped the mass in several of them using the motion of their stars and the gravitational lensing of galaxies behind them. The results line up. These little galaxies sit inside colossal invisible halos that dwarf anything expected for their size. Why would some galaxies be mostly dark matter, while others have almost none? Theories are multiplying. One idea is that these dark heavy dwarfs are the survivors of the early universe, galaxies whose halos formed first, but whose star formation was interrupted. Maybe an early burst of hot gas blew out their raw materials before many stars could form. The halo stayed, the stars never came. Another idea is that these galaxies were plundered. When small galaxies orbit inside big clusters, larger neighbors can tear off their outer stars in slow gravitational pulls. Over billions of years, this strips the visible part down to a shadow of itself. The dark matter halo, being more extended and less connected to visible matter, resists the stripping. What remains is a little leftover of stars sitting inside a still massive invisible shell. A third idea is more radical. Some astrophysicists suspect dark matter does not always gather at the same intensity. Different regions of the early universe might have had different dark matter densities, for reasons nobody yet understands. Some little patches got enormous halos. Others got almost none. Galaxies then formed inside whatever they were dealt. If that is true, the standard model of cosmology needs adjusting. It currently assumes dark matter was distributed fairly smoothly at the start, clumping up only through gravity. Patchy dark matter from the very beginning would rewrite several chapters of the textbook. Either way, the bookends are now clear. Galaxies with almost no dark matter. Galaxies with almost nothing but dark matter. Both exist, and the things that tie them together stretch further than anyone suspected. Galaxy clusters are the biggest gravitationally bound things in the universe. Each one holds hundreds or thousands of galaxies, enough gas to fill empty space between them for millions of years, and dark matter halos that stretch for incredible distances. They are islands of mass, scattered across the cosmic ocean. The islands are not alone. They are connected. Webb's surveys, combined with data from radio telescopes and other infrared observatories, have mapped the routes between galaxy clusters in sharper detail than ever before. Long ribbons of dark matter run between them, carrying gas and occasional small galaxies along their length. These are the bridges of the cosmic web. Some of these bridges stretch across distances so large that our usual units fail. The widest confirmed dark matter bridge linked by Webb analysis runs for more than 50 million light-years. 50 million. If you could travel at the speed of light from one end to the other, the trip would outlast entire civilizations. Entire species would evolve and disappear while your photon was still in transit. Along these bridges, the universe quietly moves itself around. Gas flows from emptier regions toward dense clusters. Dragged by the gravity of the dark matter rope, small galaxies drift along the strand, slowly tugged toward the larger cluster at one end. Think of it as cosmic plumbing. The bridges are the pipes. Dark matter is the pipe material. Gas and galaxies are the water. Webb has been able to sharpen one surprising detail. The bridges are not uniform. Some stretches are thick, holding enough invisible mass to rival a small cluster. Other stretches narrow down to thin threads, barely detectable in the lensing data. A few are twisted, braided, as if two smaller bridges merged partway along. One observed bridge showed what looks like a kink, a sudden bend in its path. The theorists had to sit up and look twice. A pure gravitational bridge should run fairly straight between its two anchor clusters, bending only slightly under external forces. A sharp kink implies a third influence, maybe an unseen mass lurking beside the bridge, pulling it out of alignment. Maybe a past collision that left the strand permanently askew. Astronomers have started calling these dark bridges. In most cases, the gas and dust along them glow faintly in the infrared, just enough for Webb to pick out. In a few stretches, no light shows up at all. Those stretches are pure dark matter, no normal matter riding along. Invisible rope, no flag attached. This has real consequences for how the universe grew. In the standard picture, galaxies and clusters are fed by these dark bridges. Material flows down the web, pools in the cluster, and becomes new galaxies or bigger ones. The flow is slow and steady, like sediment building a delta. If the bridges are uneven, if some of them are thicker or thinner, or kinked in ways the models did not predict, then the way matter moves through the universe has to be rethought. Clusters may grow in bursts rather than smoothly. Quiet galaxies at the end of thin strands might be starving. Ones at the junction of thick strands might be gorging. Webb has started showing us the universe's network of invisible highways. Some are wide and well paved. Some are narrow and choked. A few bend in ways no one can yet explain. The bridges connect clusters, but around individual galaxies, the shapes are getting stranger too. Webb started photographing rings that had no business being there. A dark matter halo should look like a puffy ball. That is the default picture. A smooth, three-dimensional sphere of invisible mass, thickest at the center, fading gradually outward. Galaxies sit in the middle. The halo spreads around them like a fog bank, without features, without edges, without structure. That is what the simulations produce. That is what the theory predicts. Webb has photographed something else. Around several galaxies, mostly older ones, in the nearby universe, Webb's gravitational lensing maps reveal strange ring-like patterns in the dark matter distribution. Not smooth halos, not fog banks, actual rings, concentric shells of higher density surrounded by thinner zones, layered around the galaxy like the rings of an onion. Nobody expected this. Rings like these should not form naturally in a cold, dark matter halo. The particles of dark matter, whatever they are, interact only through gravity. They should settle into smooth distributions over billions of years, not crystallize into nested shells. The first few ring detections were dismissed as noise. The second batch were harder to explain away. By the time half a dozen galaxies showed the same feature, the astronomy community started paying serious attention. One possibility is that the rings are scars from past collisions. When two galaxies collide head-on in the right geometry, they can generate ripples in the mass distribution, the way a pebble dropped in still water creates expanding circles. Gravity can do the same thing, though it is rare. If dark matter behaves the way the standard model says, those ripples should smooth out over millions of years. Yet Webb is catching clear, sharp rings. Some of them look crisp, as if frozen in place. Another possibility is more provocative. Maybe dark matter particles can interact weakly with each other through some unknown force. A small nudge between particles, too faint to matter in most situations, could add up over billions of years and create structures like rings. In that case, dark matter would no longer be the simple, non-interacting stuff of the old theory. It would have a tiny hidden chemistry of its own. Picture a huge swimming pool filled with perfectly smooth water. Drop in a heavy stone. Ripples spread outward, then die away. That is the old model. Now picture dropping the same stone into a pool where the water has a slight, invisible tension, like a molasses thinned almost to nothing. The ripples travel farther. They keep their shape longer. They leave behind concentric patterns that linger for hours instead of seconds. Some of Webb's ringed halos look like that second pool. A third idea comes from the so-called fuzzy dark matter theory. In this model, dark matter is made of extremely light particles that behave like a giant quantum wave rather than a cloud of tiny beads. Waves create ripples and nodes naturally. On huge cosmic scales, fuzzy dark matter could form ring-shaped features around galaxies as standing waves in its density. Webb's images might be pictures of those waves. No single theory has locked in. The debate is active, sometimes heated, and still unfolding at conferences. What matters is that the default picture, the boring, smooth sphere, no longer captures what we are seeing. Dark matter is showing structure, layers, shells, patterns, and in one category of galaxies, the halo is not just structured, it is dramatically lopsided, piled on one side of the galaxy like a snowdrift. A galaxy spinning in space should have a balanced halo around it. That is the baseline. The halo surrounds the galaxy like an atmosphere surrounds a planet. The density falls off smoothly in every direction. Stars in the galaxy feel roughly the same invisible pull no matter which side of the disk they are on. Balance keeps the galaxy stable. It keeps the spiral arms symmetric. It keeps the rotation steady. Webb has been showing astronomers lots of halos that are not balanced at all. In galaxy after galaxy, especially medium-sized spirals at moderate distances, the dark matter map comes out skewed. One side of the galaxy sits inside a thick, heavy pile of invisible mass. The other side has noticeably less. The center of gravity of the halo does not line up with the center of the visible galaxy. It is offset, sometimes by tens of thousands of light-years. The galaxies themselves look fine. The stars are where stars usually are. The gas is where it is supposed to be. It is only the invisible part that has drifted sideways. Picture a house sitting on a hill. The house is square and ordinary. Now, imagine that under the house, instead of a flat foundation, there is a huge pile of dirt pushed up on one side and scooped away on the other. The house is fine. It has not tipped yet, but the ground underneath it is clearly uneven. That is how these lopsided galaxies look in the Webb data. Theorists have been scrambling to explain the asymmetry. The most straightforward idea is a past flyby. If a smaller galaxy passed close to the larger one within the last billion years or so, it could have tugged the dark matter halo off-center with its gravity. The visible galaxy, denser and more compact, would barely notice. The diffuse halo, more easily disturbed, would still be sloshing from the encounter. Evidence for this idea appears in some cases. Webb has found faint streams of stars near a few of these lopsided galaxies, pointing back toward likely culprits, small companion galaxies, or the remnants of ones long since torn apart. The flyby story fits. In other cases, there is no visible culprit anywhere nearby. The galaxy sits alone in a relatively quiet patch of sky, nothing close enough, recently enough, to have pushed its halo that far off. Yet the offset is still there. That opens a stranger possibility. Maybe the halo was lopsided from the start, The universe might form dark matter halos that are not perfectly smooth balls, but irregular shapes, stretched or bent by conditions in the early cosmos. The galaxy settled into the middle of its halo, not at the center of mass, but wherever the gas first accumulated enough to ignite stars. If halos are sometimes born lopsided, again, the big picture needs updating. For decades, simulations assumed initial halos were close to spherical, with only small bumps. Now Webb is hinting that many halos may be significantly bent. The consequence matters for almost everything: the rotation of galaxies, the distribution of their satellites, the way they grow over time. A lopsided halo drags on its galaxy differently than a balanced one. Stars orbit through denser and thinner zones as they circle. Gas flows in uneven currents. None of this showed up clearly before Webb. Older telescopes could hardly detect halos at all, let alone tell if they were tipped. And while the mid-sized galaxies are showing wonky halos, the smallest galaxies Webb is studying are hiding an even wilder secret. Some of them are almost pure dark matter, with just a whisper of light. Some galaxies barely glow at all. They are the ghost galaxies, dwarf systems so faint that from our vantage point, they look like faint smudges against the black sky. A few thousand stars, a little gas, a weak glimmer of ancient starlight. Against the brightness of the Milky Way, they are practically invisible. Yet many of them are among the heaviest small objects in the universe. Webb has confirmed a pattern suspected for years. Dwarf galaxies, especially the faintest ones, are packed with dark matter. Ratios of 100 to 1, 200 to 1, sometimes higher, of invisible mass to visible mass. If you weighed the entire galaxy and set aside everything you can see, the leftover would dwarf the rest. Take a galaxy like Segway 2, a ghost orbiting the Milky Way. Not far cosmically speaking, it holds only about 1,000 stars. Its glow is so faint that astronomers had trouble confirming it was a real galaxy at all. Webb's sharp infrared eyes measured its stellar motions more accurately than ever. The stars move far too fast to be held together by their own small mass. The gravitational pull keeping Segway 2 intact must come from an enormous invisible halo. Estimates suggest the dark matter in Segway 2 outweighs the starlight by a factor of roughly 300. Imagine walking into a small cottage and discovering that hidden in the walls, under the floor, and above the ceiling is a lead vault weighing 300 times more than the entire cottage itself. From the outside, it is just a little house. Inside, almost nothing. The mass is locked into the shell, invisible to anyone just looking. Webb has found and remeasured dozens of such dwarfs, both near our galaxy and in nearby galaxy groups. Many of them match or exceed these dark matter-to-light ratios. A few appear to have even higher proportions. Although the measurements are tricky and the debates continue, why would the universe make such objects? Several theories try to explain them. One theory holds that these dwarfs are fossils from the early universe. Before big galaxies fully assembled, the universe was full of tiny clumps of dark matter. Some managed to catch small amounts of gas and ignite a handful of stars before being engulfed by larger galaxies. Others stayed small, stayed dark, and drifted quietly through cosmic history. Webb may be looking at actual relics of the early cosmos, little time capsules preserved for nearly 14 billion years. Another theory says these dwarfs were originally larger galaxies that got stripped down. Tidal forces from a bigger neighbor can peel off the outer stars of a dwarf, leaving just the compact core. The dark matter halo, being more extended, is also stripped, but at a different rate. Over time, a once ordinary dwarf can lose almost all its stars and keep a disproportionate amount of its invisible mass. Whichever explanation is right, the presence of these dark matter-heavy dwarfs is one of the strongest clues that dark matter exists. Without it, these tiny galaxies would fly apart under the motion of their own stars in a single cosmic instant. Yet they sit there, stable, silent, glowing just enough for Webb to measure them. Little glowing shells wrapped around mountains of the unseen. Dark matter seems content to build these dim, heavy fossils. But when two big clumps of it smash into each other at cosmic speed, the behavior gets stranger still. When two ordinary things collide, they push against each other. Two cars in a crash deform, bounce, lose speed. Two clouds of gas, meeting at high speed, heat up and slow down. Even tiny particles like photons, when crowded together, nudge each other around. Every familiar kind of matter resists being shoved through itself. Dark matter, from what Webb has shown us, barely resists at all. Astronomers have long studied galaxy cluster collisions to probe this question. The Bullet cluster was the first great example, but it was not the last. Several other famous collision systems have been imaged by Webb in the past couple of years, and the results are consistent in a way that is both thrilling and unsettling. In each collision, the galaxies pass through one another. The gas slams together and heats up, and the dark matter simply keeps going. Two invisible masses can sail straight through each other at extreme speeds, emerging on the far side as if the collision had never happened. Webb's improved lensing allows astronomers to measure how much the dark matter slowed in each collision. The answer is very little. In some cases, no measurable slowing at all. Two invisible mountains, each containing trillions of suns worth of mass, fly through one another like two swarms of ghosts, barely brushing as they pass. This is the strongest confirmation that dark matter, whatever it is made of, interacts extremely weakly with itself. Its particles almost never bump, never scatter, never lock into each other. They travel in straight lines through space, responding only to the distant tug of gravity. Picture a blizzard of snowflakes sweeping across a field. Now imagine those snowflakes can pass through each other without a single collision. Two blizzards could meet head-on, and the snowflakes would simply slide past. No piling, no melting, no whisper of contact. That is how the dark matter in these cluster collisions behaves. The evidence has important consequences for the hunt for dark matter particles. Many leading candidates, like certain kinds of weakly interacting massive particles, predict a very faint chance of self-collision. Too much self-collision would ruin the cluster data. Too little would imply something almost purely gravitational. Webb's collision images are pushing the limits on how much self-interaction is allowed. At the same time, a few analyses have noticed slight hints that dark matter in some collisions may have scattered very faintly. The dark mass does not quite track perfectly with the galaxies. It seems to fall behind, almost imperceptibly. If that hint holds up across more observations, it would be the first sign of a new kind of force, a ghost force, acting among dark matter particles alone. This possibility has energized a whole subfield of research. Several theorists have proposed that dark matter might have its own shadow physics, complete with dark forces and dark particles that interact only with each other. Normal matter would barely notice. We would only see traces in the way dark matter moves during extreme events like cluster collisions. Webb cannot resolve this question on its own, but it can watch a growing gallery of cosmic crashes and tell us how invisible mass moves through itself. So far, it moves almost freely. Almost. That almost is the doorway, a slightly open door into a hidden part of physics. And behind that door, new hints have started to show up. A cluster named Abell 3827 sits about 1.5 billion light-years away. It is a crowded pile-up of galaxies, dominated by 4 bright central ones, with many smaller galaxies orbiting around them. For years, this cluster has been a favorite target for dark matter research, because its tight, busy core makes it easier to measure how mass and light line up. Something in Abell 3827 has always looked slightly off. One of the 4 central galaxies appeared to have its dark matter halo offset from the galaxy itself. The invisible mass was not sitting neatly underneath the starlight. It was lagging behind, trailing the galaxy as if dragged by some gentle friction. The offset was small, but real. For a while, it was the best hint that dark matter might not be entirely frictionless after all. Then Webb stared at Abell 3827 with its full infrared power. The new images sharpened everything. Faint background galaxies that had been mere blurs in older data popped out as clean ovals. The lensing map became finer, the mass distribution more detailed, the statistical uncertainties smaller, and the offset survived, strengthened, even. The dark matter behind that particular galaxy is clearly lagging. Some analyses put the displacement at around 5,000 light-years, small on cosmic scales, huge on human ones, enough to strongly suggest that something is slowing the halo relative to the galaxy it belongs to. If the offset is real, it means dark matter has a tiny amount of self-interaction. The particles making it up are not perfectly slippery. When they pass through one another, they scatter just a little. Over the chaos of a galaxy cluster, with many flybys and collisions happening at once, this faint drag adds up. Halos slip behind galaxies, mass smears out, invisible stuff gets tugged by invisible stuff. Not every astronomer is convinced. Some argue that the lag might be explained by foreground effects, by other nearby halos pulling the mass off-center, or by imperfect modeling of the cluster's complicated shape. Independent analyses of Abell 3827 have produced different numbers, sometimes larger offsets, sometimes smaller, occasionally none. Yet Webb is finding similar hints elsewhere. In a handful of other clusters, the dark matter appears to lag by tiny amounts behind its galaxies during recent or ongoing interactions. One cluster shows a small tail of invisible mass trailing a galaxy like the wake behind a boat. Another shows a central dark matter clump slightly displaced from its brightest galaxy. Individually, each case can be argued away. Collectively, a pattern is forming. Physicists have long studied models called self-interacting dark matter, in which dark particles can scatter off each other through some hidden force. These models were built to solve some old problems in galaxy simulations, like why dwarf galaxies have flatter cores than simple theory predicts. If Webb is catching tiny drag effects in multiple clusters, it would fit these models well. The idea opens strange doors. A hidden dark force means a hidden set of dark particles possibly mediating it. A hidden particle means a whole new layer of reality, operating in parallel to the one we see, visible only through gentle effects on cluster-scale mass. It is the first faint whisper that dark matter might have a social life. It might push, tug, and nudge its own kind, just barely. And if it does, the grand structure of the universe, the cosmic web, will start looking less like a static skeleton and more like a pulsing, living thing. Step back far enough, and the universe stops looking like galaxies at all. At the largest scales, galaxies are just glitter. The real structure is a vast, tangled web of dark matter, stretching in every direction, filling all of space. Thick strands where clusters live, thinner threads where small groups form, huge empty voids where almost nothing exists. This is the cosmic web, and Webb has been photographing more of its skeleton than any telescope in history. The web was predicted long before it was seen. Simulations in the 1980s and 90s showed that cold, dark matter would naturally arrange itself into a filament-rich structure as the universe expanded. Galaxies would form at the densest junctions. Long bridges would link them. Voids would yawn between them. It was elegant math waiting for evidence. Hubble and ground-based surveys like the Sloan Digital Sky Survey confirmed the broad shape. Galaxy counts matched the predicted pattern. The universe did have a web-like structure, but the resolution was blurry. The thin parts of the web, the dark matter strands with little visible matter on them, could only be guessed at. Webb has changed that by going faint and far. It can detect lensing effects from light that is so old and so dim that other telescopes missed it. With Webb's help, astronomers have now mapped dark matter in regions that previously looked like blank patches of sky. The new maps are stunning. Imagine lighting up a spider web in a dark basement with a sudden flashlight. Suddenly you see not just the big structural strands, but all the smaller threads branching between them. You see how the web is anchored to beams. You see how the pattern goes all the way to the ceiling. That is roughly how astronomers describe the view through Webb. Smaller filaments that had only been implied now show up in detail. The connections between clusters are more numerous and more complex than older maps suggested. Some clusters, once thought to be relatively isolated, are now seen to be tied to half a dozen smaller filaments feeding them from every direction. A few features of the new web maps are especially striking. First, the voids are emptier than expected. Huge spherical regions of near nothing, stretching for hundreds of millions of light years in every direction, hold fewer galaxies and less dark matter than older surveys implied. The universe has bigger, empty rooms than we thought. Second, the junctions are more tangled. Where filaments meet, they often cross at strange angles, twist around each other, or merge into knotted plateaus. Clusters at these junctions appear to grow faster, fed by multiple streams at once. Third, parts of the web appear to be already coming apart. As the universe accelerates its expansion under the influence of dark energy, the cosmic web is being stretched. Some bridges between clusters are thinning out, others are quietly detaching. Webb is seeing a structure that is not only massive but slowly aging. The cosmic web is the frame on which galaxies hang. Without it, everything would fly apart. With it, every galaxy sits on a kind of cosmic trellis. Thanks to Webb, this trellis has a face. Its bones are visible, its joints are mapped, its missing pieces are marked. Some of the most startling maps, though, focus on the empty parts, the voids, where almost nothing should be, and where light itself seems to behave oddly. The voids are the biggest empty things in the universe. They are enormous, nearly spherical regions of space where galaxies are scarce, gas is thin, and dark matter is far less concentrated than the cosmic average. Some voids span over 200 million light-years across. A few are even larger. Inside them, the density of matter of all kinds drops to a small fraction of what exists in galaxy-rich regions. You would think the voids are boring. Astronomically, they are anything but. Webb has taken a new interest in these empty zones, partly because voids are excellent laboratories. With fewer galaxies and less dark matter in the way, the light from background objects should travel almost undisturbed. Whatever warping does appear in that light tells you something about whatever sparse matter is present, and about the physics of the universe itself. Some of the new void observations have produced unexpected results. In several voids, Webb has found that background galaxies are distorted slightly more than expected given how little mass should be present. Something is bending the light just a bit too much. Analyses suggest a few possibilities. Either there is more dark matter hidden in these voids than the standard model predicts, or light itself is behaving in slightly unusual ways across such vast, empty stretches. If hidden dark matter is the answer, it raises the question of why it is there at all. Voids are supposed to be underdense, yet a thin mist of unseen mass consistently showing up across multiple voids would imply that dark matter is harder to clear out than theory says. Some form of low-level dark fog might be drifting through even the emptiest parts of the universe. If the answer is weirder light behavior, the consequences are bigger. Modified gravity theories, which try to explain cosmic motion without relying on dark matter, often predict small deviations in how light travels through very empty regions. Webb's void data has given these theorists new numbers to chew on. A few of them are finding that their models match the observations surprisingly well in void regions, even when they fail in crowded clusters. Other studies have looked at the so-called cold spots. These are specific regions in the cosmic microwave background, the faint afterglow of the Big Bang, where the temperature is slightly lower than average. One famous cold spot sits behind a giant void. Light from the early universe passing through that void appears to have been affected in a way that does not line up cleanly with standard predictions. Webb cannot see the microwave background itself, but it can map the nearer structures along the same line of sight. The new maps help narrow down what might be causing the cold spot. So far, nothing fits perfectly. Some physicists have started wondering aloud if the cold spot is a hint of physics beyond the standard story, a very distant structure, a bizarre patch of dark energy, even, in the wildest speculation, a trace of collision with another universe. None of those ideas are close to proven. All of them sound strange spoken out loud, yet the data is weird enough that they get discussed. Voids were once considered the boring parts of the sky. Webb has helped reveal that they are anything but. They are the emptier regions of a universe that has hidden density where it should not be, and hidden physics where there should be nothing to see. That pattern of the universe refusing to behave the way textbooks say keeps showing up. Webb has also sharpened a question older than Webb itself. Why are entire galaxies spinning in ways Newton's laws cannot explain? This was the mystery that first made dark matter real for everyone. Long before Webb, long before Hubble, Vera Rubin was the one who pushed the problem into the mainstream. She measured how stars at different distances from a galaxy's center moved through space. The pattern her data showed became known as a galaxy's rotation curve. Under Newton's laws, applied the way they are used in our own solar system, a rotation curve should have a clear shape. Stars close to the galactic center should move fastest, because most of the mass is there. Stars farther out should move slower, because they are farther from the pull of that central bulge. This is exactly how planets orbit the Sunday Mercury sprints. Neptune crawls. Galaxies refuse to play by those rules. Rubin found that stars at the outer edges of galaxies were moving almost as fast as stars near the middle. The curves went flat instead of dropping off. If only the visible matter existed, these outer stars should have been flung into space long ago. Something invisible had to be pulling on them. Dark matter was the answer, an enormous halo surrounding each galaxy, extending far beyond the stars, with mass in the right places to keep those outer stars moving quickly. For decades, rotation curves were measured mostly in visible and radio light, with ground-based telescopes and with Hubble. The flat curve pattern was confirmed again and again across hundreds of galaxies. The standard story held up. Webb has pushed the measurements further and sharper than anyone thought possible. With its infrared sensitivity, Webb can measure the motions of stars and gas clouds far out at the edges of galaxies, in regions where the light is so faint that older telescopes could barely see anything at all. At these extreme distances, the rotation curve should reveal the true edge of the halo, the point where dark matter finally thins out and the flat curve begins to drop. Several Webb surveys targeted nearby spiral galaxies for exactly this purpose. The results are striking. In many cases, the rotation curves stay flat for even longer than previously thought. The halos extend further. The invisible mass is more spread out than the standard simulations predicted. In a few galaxies, Webb has also caught subtle wiggles in the rotation curves. Instead of a smooth, flat line, the velocities show small bumps and dips at certain radii. These wiggles, if confirmed, could mean the halo is not smooth, but contains denser and thinner shells. Another hint of structure, where none was supposed to exist. Rotation curves are also the main battlefield for modified gravity theories. Theorists in the modified Newtonian dynamics, or MOND, camp have long argued that the flat curves of galaxies could be explained by a small change to Newton's laws at very low accelerations, without the need for dark matter. Their models make specific predictions for how curves should look in the far outskirts of galaxies. Webb's new data is testing those predictions directly. Some galaxies fit the MOND predictions remarkably well. Others fit the dark matter picture better. A few fit neither cleanly, leaving theorists scratching their heads and drawing new equations on the board. The bottom line is that galaxies keep spinning in ways that cannot be explained by the visible mass alone. Webb is confirming and sharpening the greatest mystery of astrophysics. What is holding these swirling disks together against gravity's own rules? Rotation curves forced the question of dark matter to be asked. Webb is forcing the question to be asked more precisely than ever. And when it looks back to the earliest galaxies, the answers only get stranger. The early universe was supposed to be slow. In the standard story of cosmic growth, the first several 100 million years after the Big Bang were a quiet time. Tiny ripples in the density of matter were just starting to pull themselves together. Dark matter, being the heaviest stuff around, led the way. Small halos formed first. They merged slowly. Bigger halos grew from many smaller ones over billions of years. Galaxies were supposed to follow this gradual recipe. Stars would ignite inside small halos. Mergers would add more stars. Over time, small galaxies would clump into bigger ones. The process was expected to take a long time. Nothing big, nothing grown up, should appear in the first 500 million years of cosmic history. Webb looked at that era and found large galaxies already there. The telescope was designed, in part, to capture the faint infrared light of the earliest galaxies. Light from those distant objects has been stretched by the expansion of the universe, shifted so far toward the red that only an infrared detector can see it. Webb's first deep images into this epoch produced astonishment. Galaxies showed up at distances corresponding to only a few 100 million years after the Big Bang. Some of them were much bigger than the models predicted. A galaxy's size implies a certain halo size. A bright, massive galaxy needs a hefty dark matter halo to have formed around. If Webb sees a galaxy that looks like it has 100 billion stars worth of mass at an age when halos were supposed to be much smaller, something about halo growth is off. The discrepancy is not subtle. In several cases, the galaxies Webb is finding at great distances have estimated masses in the range of tens of billions of solar masses, at a time when the most massive halos in standard simulations should only reach a fraction of that. Each early galaxy implies an enormous invisible halo already in place, far ahead of schedule. Different teams have tried to explain this. Some suggest that early galaxies formed stars far more efficiently than expected, packing a lot of light into a small halo. That would soften the problem, but only a little. Even efficient star formation cannot make a small halo look like a big one in all their measurements. Others propose that the timeline for halo growth needs to be adjusted. Perhaps dark matter clumped more aggressively in the early universe than we thought. Perhaps the initial ripples were not as small as predicted. Perhaps some halos grew through pathways that simulations have underestimated, like rapid mergers or denser than expected starting conditions. A few theorists have gone further, arguing that Webb's early galaxy problem could point toward new physics entirely. Perhaps dark matter is warmer than the cold dark matter model assumes. Perhaps some kind of early dark energy gave growth a head start. Each possibility rewrites part of the cosmic story. To picture the puzzle, imagine arriving at a construction site expecting to find workers laying a foundation. Instead, you find a 5-story building already standing, fully wired, with people inside. You know roughly how long the project has been running. That time is not enough to build what you are seeing. Either construction started much earlier than you were told, or the crew worked at superhuman speed, or someone rewrote the blueprints without telling you. Webb is staring at the cosmic equivalent, enormous halos and galaxies where small ones were expected. The blueprint of the universe is being redrawn on the fly. The galaxies themselves are the physical part of this puzzle, and when Webb zoomed in on some of them, the view got stranger still. Some of the galaxies Webb found were not just there, they were mature. When the telescope first started observing the most distant reaches of space, astronomers hoped to find young galaxies just getting started. Blue, patchy, chaotic systems with clumps of newborn stars and bursts of hot gas. The nurseries of the early universe. That is what simulations predicted should dominate the view. Some of what Webb found matched that picture. Plenty of young, irregular galaxies showed up at extreme distances, but alongside them sat a handful of truly bizarre objects. Galaxies that looked old, structured, organized, already resembling the kind of large, settled galaxies we see much closer to home. A few of these stood out so strongly that they were nicknamed impossible galaxies. One of them has the designation JWST ER1G. It appears at a redshift, suggesting it existed when the universe was only around 2 billion years old. From this era, astronomers expected to see small, messy clumps still merging into shape. Instead, JWST ER1G is compact, massive, reddish in color, and mature in its starlight. It already looks like a modern elliptical galaxy, the kind of galaxy that usually takes many billions of years of mergers to form. The shocker came when astronomers measured its gravitational effect on a background object. JWST ER1G sits in front of a distant galaxy, and its gravity creates a near-perfect Einstein ring around the background light. The ring allowed a direct measurement of JWST ER1G's total mass. It turned out to weigh many hundreds of billions of suns, a giant in any era, let alone a time when the universe was supposed to still be under construction. That mass implies a dark matter halo of matching heft, formed remarkably early. a giant invisible cocoon already in place, already hosting a fully assembled galaxy inside it. Several other impossible galaxies have joined the list. Some of them are far more massive than models allow. Some are too red, meaning they stopped forming stars long before such galaxies were expected to exist. Some are surprisingly small in size, packing enormous mass into a volume that stuns astronomers used to more typical densities. Each one implies the same thing. Big dark matter halos appeared fast. Galaxies grew inside them faster than the timeline allowed. Some of them even aged, finished their star formation, and settled into quiet middle life while other galaxies were still being born. Picture a small town that was supposed to be empty land 50 years ago. You arrive at the town today and find not only modern houses, but a few stately mansions that were clearly built decades ago, with mature trees and weathered paint, already looking like historic buildings. The timeline says none of it should exist yet. The houses are clearly there. That is the mood of the impossible galaxy problem. The explanations circulate. Maybe star formation ran at extreme efficiency in the earliest halos. Maybe heavy gas flowed in faster than models predicted. Maybe massive black holes seeded some of these galaxies early, helping them grow in weird bursts. Maybe the dark matter halo mass function was skewed toward larger halos in the earliest epoch. More than one team has also quietly raised a bigger possibility. Maybe the standard cosmological model itself, including the assumed behavior of dark matter, needs modification at high redshift. If halos grew faster than the current model allows, something fundamental is off. Either way, these ancient galaxies are dark matter time machines, and the halo's web is finding around them are only one kind of invisible mass showing up where it should not. Even smaller clumps are appearing in places nobody predicted. The standard cold dark matter theory has a crisp prediction about clumps. Dark matter, the theory says, should clump at every scale, from huge cluster-wide halos down to tiny halos hosting individual dwarf galaxies. Gravity should produce a wide range of nested structures. But the theory also has a limit. Below a certain size, clumps should be rare. Very small halos, with masses around 1 million suns or less, should exist only in modest numbers. Extremely small halos, much smaller than that, should be almost non-existent. This prediction matters because it is testable. If someone found lots of tiny halos, especially ones with no visible galaxies inside, the standard theory would need to change. Webb has started producing exactly that kind of evidence. One of the key observations involves a technique called flux ratio anomalies. When a distant galaxy is gravitationally lensed by a foreground galaxy, its light splits into several images, each one a warped copy of the original. The relative brightness of those copies depends on the detailed mass distribution of the foreground galaxy. If there are hidden small clumps of dark matter inside or near the lens, they can subtly shift the brightness of the multiple images. Before Webb, this technique relied mostly on Hubble and radio observations. The results hinted that small dark matter clumps were more common than expected. Webb's infrared sharpness has boosted these measurements dramatically. By capturing the multiple images of distant galaxies with higher precision, Webb can detect the gravitational footprint of much smaller clumps than before. Analyses of several lensed galaxy systems have now revealed the presence of compact dark matter lumps with masses well below those predicted to be common. Some have estimated masses comparable to a modest globular star cluster, even though no light comes from them at all. Another line of evidence comes from stellar streams. These are long rivers of stars in the outer halo of our Milky Way, left behind by dwarf galaxies that were shredded by gravity long ago. A stream should look like a smooth line of stars along its path, except real streams show gaps, kinks, and thinner regions. Astronomers have long suspected these gaps are caused by invisible dark matter clumps drifting through the streams. Each clump's gravity pushes aside some stars as it passes, leaving a blank spot. Webb has improved the measurement of stream features, especially in fainter and more distant streams in the Milky Way's halo. The number of gaps and their sizes support the idea of many small dark matter clumps out there, far more than the standard theory comfortably predicts. Think of walking through a cornfield at night. In the dark, you cannot see the farmer, but you can tell something passed through by the trampled stalks. A few trails mean a few passes. Many trails, scattered in different directions, mean many passers-by. Webb is finding many trails in the starry grass of our galactic halo. If small dark matter clumps are abundant, several theories get a boost. One option is warm dark matter, in which the particles move a bit faster than in the cold dark matter model. Warm dark matter would suppress the smallest clumps, so if we see lots of them, warm models lose ground. Alternatively, fuzzy dark matter, cold but quantum wave-like, would predict a different pattern altogether. The exact fit is still being worked out. What is clear is that the universe has dark matter clumps in places and sizes the standard theory did not cleanly predict. And that gets us into one of the most heated debates in cosmology today. Is dark matter really cold, or is it warmer than we thought? For decades, the cold dark matter model won almost every battle. The word cold in its name does not refer to temperature in a direct sense. It refers to how slowly the dark matter particles were moving at early times. If particles move slowly, they clump easily at small scales, producing many small halos. If they move quickly, they wash out small-scale structure, leaving only large halos. Cold dark matter was preferred because it matched the observed pattern of galaxies at large scales. Warm dark matter, with its faster particles, was often dismissed because it seemed to wipe out too many small structures. It could not produce as many dwarf galaxies as we see. Webb's observations have stirred this up. On one hand, Webb is finding more small dark matter clumps than the simplest cold dark matter model predicts, especially in stellar stream gaps and lensing anomalies. That seems to favor cold dark matter, or even a model with extra small-scale structure. On the other hand, Webb is finding big galaxies and massive halos forming too fast in the early universe, which is harder to explain in standard cold dark matter. Warm dark matter models, in certain versions, can allow faster early growth of the largest structures while suppressing the smallest ones. Depending on the flavor of warm model, some early galaxy observations fit more comfortably. The result is a modern puzzle. Different Webb findings seem to pull in different directions at the same time. Small-scale data point toward more structure than expected. Large-scale early universe data point toward bigger and faster structure than expected. Cold dark matter has to work overtime to fit both. Simple warm dark matter struggles to fit either by itself. Theorists are responding with hybrid models. Maybe dark matter has a small warm component mixed with a cold majority. Maybe it has internal interactions that only matter at certain scales. Maybe some kinds of dark matter particles are cold at early times and become warm later, or vice versa. Every combination is being tried against Webb's growing catalogue. To make the tension concrete, imagine the universe as a bowl of soup cooling in front of you. If the soup is mostly cold, you would expect it to settle into small, cloudy swirls. Little eddies everywhere, finely structured. If the soup is warmer, swirls smooth out, and only big currents remain. Webb is showing you a bowl with both fine swirls and unusually strong big currents. No simple temperature setting reproduces what you see. Several upcoming experiments will focus on narrowing this down. Deep, high-resolution lensing surveys will try to pin down exactly how many small halos exist. Galaxy surveys at extreme distances will map the growth of structure across cosmic time. Theoretical work will fine-tune the predictions of different dark matter flavors, making them easier to test. What is no longer in doubt is that the simple, cold, dark matter story is under pressure. For years, it was the unchallenged default. Now, thanks to Webb, astronomers are again seriously asking whether dark matter is a little warmer or a little more complex than the textbooks say. The debate has been quietly reopened. Nobody is declaring an answer yet. But the temperature of the discussion has risen. And in the smallest galaxies, where dark matter dominates, Webb is noticing something that makes this debate even weirder. Dark matter might not be particle-like at all. In some places, it seems to be behaving like a fluid. Inside some of the universe's smallest galaxies, the math gets strange. Dwarf galaxies have always been one of the best places to probe dark matter, because they are so dark matter dominated that the visible stars almost act like tracer particles riding through an invisible ocean. Tiny differences in how the stars move can reveal subtle properties of the ocean. For years, astronomers noticed a puzzle called the core cusp problem. Simple, cold, dark matter simulations predicted that dwarf galaxies should have sharp peaks of dark matter density right in their centers, a narrow spike of invisible mass. Real dwarf galaxies, as best as anyone could measure, looked different. Their centers were flatter, softer. The density did not spike, it plateaued. The difference might seem technical, but it has big consequences. A sharp cusp of dark matter would grip inner stars tightly. A flat core would let them wander more freely. The core cusp problem is a quiet mismatch between theory and observation, hinting that something about the behavior of dark matter is not being captured. Webb has been measuring dwarf galaxies with unprecedented precision. Its infrared sensitivity lets astronomers catch the faint motions of individual stars in systems that were barely visible before. The core cusp mismatch, instead of going away, has gotten sharper. Many dwarfs show flat central regions where theory wanted spikes. This is where the fluid idea comes in. Some theories propose that dark matter is not made of regular particles, but of ultralight quantum objects that can overlap with each other in huge, coherent waves. At galactic scales, this kind of dark matter behaves less like a cloud of dust and more like a single giant fluid, a sloshing ocean filling the galaxy. Its density cannot spike to a sharp point because wave physics forbids it. Instead, it smooths itself into a central plateau. Webb's measurements of dwarf galaxy cores fit several versions of this picture reasonably well. The flatness of their centers, the slight wiggles in their rotation curves, even certain ring-like features in lensing, all match predictions of fluid-like dark matter models. Other possibilities exist. Self-interacting dark matter, where particles scatter off each other gently, can also produce flat cores over time. Complicated feedback from stars and supernovae can also reshape a halo's center, though simulations have long struggled to make this work cleanly in the smallest dwarfs. To picture the fluid version, imagine dropping a heavy weight into a pool of mercury. Mercury, being dense and liquid, does not let the weight sink smoothly. It pushes back, it smooths over the spot. You end up with a gentle dip in the mercury's surface rather than a sharp hole. That is how ultralight dark matter, as a quantum fluid, would treat any attempt to form a sharp density spike. It would push back and smooth things out. In this picture, galaxies float inside gentle, invisible oceans, rather than sitting inside clumpy, invisible dust clouds. Every galaxy is a boat on a dark sea. The sea has waves, tides, and currents we are only beginning to sense. The fluid interpretation is not yet the leading theory. It has its supporters and its critics. What is clear is that Webb's dwarf galaxy measurements have strengthened the case that dark matter is not behaving like simple cold dust particles on the smallest scales. Something softer, wavier, more liquid is at play, and some of the strangest candidates for this fluid-like dark matter show up in a class of galaxies Webb has been studying in detail. Ghostly, oversized, barely there galaxies that float inside clusters like cosmic jellyfish. Ultra-diffuse galaxies should not exist, yet the universe is full of them. These galaxies are about the size of the Milky Way in physical extent. Some are even bigger, but they contain far fewer stars, spread so thinly through their volume that they are nearly invisible. If you tried to photograph one from a nearby galaxy cluster, it would show up only as a faint haze, almost lost against the dark sky. Ground telescopes barely detected them. Hubble managed to find several hundred inside big clusters. Webb has taken the hunt to a new level. Its infrared sensitivity and high resolution have revealed thousands more, some lurking in places no one expected. These galaxies are astronomical puzzles in themselves. A galaxy the size of the Milky Way, with only 1% of its stars, should be torn apart by the tidal forces of the cluster it lives in. It should not hold itself together. Yet ultra-diffuse galaxies persist, often for billions of years, surviving within the violent environment of galaxy clusters. The only explanation most astronomers can find is massive dark matter halos. Some ultra-diffuse galaxies appear to have halos comparable to those of fully grown galaxies like our own, despite having a tiny fraction of the stars. Others, like the famous NGC 1052 DF2, seem to have almost no dark matter at all, making them the opposite extreme. The mismatch between these two kinds of ultra-diffuse galaxies is one of the richest puzzles Webb is now exploring. A few ultra-diffuse galaxies Webb has photographed look especially bizarre. Their stars are arranged in soft, cloudy blobs, without spiral arms or clear disks. The galaxies drift through cluster space like delicate soap bubbles, somehow intact despite the gravitational chaos around them. Some of them have unusually long tails of stars trailing behind, as if they are being gently dragged through the cluster gas. Webb's measurements suggest that many of these ghostly systems sit inside halos, heavy enough to shield them from being torn apart. Inside that shielding, the stars can drift without being stripped. The outer halos absorb the abuse, while the stars stay relatively undisturbed. Imagine carrying a light, fluffy cloud of cotton through a crowded room. If you hold it in your bare hand, it gets crushed almost immediately. Now imagine surrounding it with a tough, invisible force field. The cloud can drift through the room, bumped and jostled, and still keep its shape. The force field absorbs all the hits. That is how an ultra-diffuse galaxy seems to survive inside a busy cluster. Some astronomers suspect that ultra-diffuse galaxies might be the missing pieces in our inventory of cosmic structure. Standard simulations predict that the universe should have far more dwarf and medium-sized galaxies than we currently see. Many of these predicted galaxies may actually be ultra-diffuse, too faint to be catalogued easily. If so, they could resolve part of the so-called missing satellites problem, in which theory predicts more dwarf galaxies than we observe. Webb is helping sort this out. By counting ultra-diffuse galaxies in more clusters and measuring their dark matter halos, it can test whether these ghost galaxies account for the missing population. Early results suggest yes, at least partially. The universe is not missing galaxies so much as hiding them in plain sight, each one a soft cloud wrapped around a thick shell of invisible mass. Ultra-diffuse galaxies are only one example of unexpected clumpiness in dark matter. As Webb keeps mapping, the patterns keep surprising. Dark matter, it turns out, likes to group itself in ways no model fully expected. Across the full range of Webb's observations, one theme keeps reappearing. Dark matter does not seem to distribute itself the way the simplest models say it should. On the smallest scales, it has cores instead of cusps. On mid-scales, it forms halos that are sometimes lopsided, sometimes ringed, sometimes oddly detached from their galaxies. On large scales, it forms webs with unusual filament shapes, voids with hidden mass, and cluster bridges with kinks. The pattern is bigger than any single observation. Dark matter, in Webb's hands, seems to prefer clustering in ways the standard cold dark matter picture did not fully anticipate. One quiet but important hint comes from statistical studies of halo shapes. For years, simulations predicted that halos around galaxies should be close to round, with slight bumps. Observations before Webb supported this, mostly. But with Webb's higher resolution lensing, a growing sample of halos is showing stronger deviations from sphericity. Many of them are elongated. Others are clearly asymmetric. Some look like potato shapes rather than soccer balls. Another pattern shows up in how halos are oriented relative to their galaxies. In theory, the major axis of a galaxy should line up, very roughly, with the major axis of its surrounding halo. Because both formed from the same cosmic flow, Webb's data shows many galaxies whose halos are significantly tilted from the axis of the visible galaxy. In some cases, the halo is rotated almost sideways, as if spinning on a different plane than the stars inside it. If halos and their galaxies are often misaligned, something rearranged them after formation. Possibly mergers, possibly strong encounters, possibly something more exotic. A third hint comes from cluster-scale maps. Some clusters studied by Webb show dark matter concentrations that do not match the brightness distribution of galaxies at all. Bright clusters often have their peak dark matter a little off from the peak galaxy density. The offsets are small but consistent, mirroring the smaller scale drifts already observed in collisions and offsets around individual galaxies. If you zoom out far enough, the universe's dark matter starts to look like it has its own preferences. It does not just passively follow where the galaxies are. It clumps, tilts, drifts, and bulges in ways that hint at a richer inner life. Picture a piece of iron sprinkled with tiny compass needles. Drop a magnet into the mix. The compass needles, you would expect, would neatly line up with the magnet's field. Yet when you look closely, some needles are tilted. Some are sliding slightly off the magnet. A few are clumped in odd patterns that do not match the field at all. Something else, some extra influence, is at play. Webb's dark matter maps feel like that. The gravitational field of galaxies should shape everything in a predictable way. Yet the invisible clumps seem to listen to additional cues we cannot yet name. The simplest extra cue would be some hidden property of dark matter itself, a small self-interaction, a slight wave-like behavior, a richer particle structure than the simple cold model assumed. Any of these would produce subtle deviations from the standard clumping pattern. The fact that Webb is seeing those deviations on so many different scales, in so many different systems, has changed the mood of cosmology. Before Webb, small anomalies could be dismissed as measurement noise. After Webb, they are starting to line up into a pattern, and a pattern is much harder to ignore than a single odd data point. Dark matter might have personality, quiet, gentle, mostly invisible, but real, and in some of the strangest corners of theory, dark matter might even power stars. Imagine a star that burns without hydrogen. Most stars, including our Sun, produce their energy through nuclear fusion at their cores. Hydrogen atoms slam together to form helium, releasing huge amounts of energy in the process. This is how stars have shone for billions of years. No fusion, no star. A wild idea, first proposed over a decade ago, imagined a different kind of star for the early universe, one that does not need fusion at all, one powered instead by dark matter. These hypothetical objects are called dark stars. Here is how they would work. In the very early universe, regions of high dark matter density might be so extreme that dark matter particles regularly collide with each other. Under certain theories, these collisions would annihilate the particles, turning their mass directly into energy, massive amounts of it. If a cloud of ordinary gas formed in the middle of such a region, the dark matter annihilation could heat the cloud enough to make it glow as a star, without any internal fusion at all. Dark stars, if they existed, would be colossal. Some models predict they could grow to tens of millions of times the mass of our Sun, far larger than any conventional star. They would glow in infrared, not visible light, since most of the energy released by dark matter annihilation would heat their outer gas rather than fuse it. For years, dark stars were an elegant but untested idea. Then Webb started observing the early universe in detail. Recent analyses of several extremely distant objects spotted by Webb have raised eyebrows. Some of them look like unusually compact, unusually bright galaxies at cosmic dawn. Their spectra, the fingerprints of their light, are strange. They lack some of the features expected from a galaxy full of ordinary stars. Instead, they look like giant single objects, glowing smoothly in infrared. Several physicists have proposed that a small number of these could actually be dark stars rather than galaxies. 3 candidate objects, in particular, have been discussed in published papers as possibly fitting dark star predictions better than conventional galaxy models. Their masses are huge, their sizes are compact, and their light patterns match rough dark star expectations. The claim is controversial. Most astronomers think these candidates are more likely to be compact galaxies or extreme early star clusters, but the fact that dark stars are even on the table, in serious papers, shows how far the conversation has shifted. To picture a dark star, imagine a vast, glowing cloud of gas the size of a small galaxy. At its heart is not a core of fusion, but a region where invisible particles keep colliding and destroying each other, releasing pure energy. The cloud glows from the inside, fed by this ghostly furnace. It shines for as long as the dark matter keeps feeding it. If dark stars are real, they would be among the earliest luminous objects in the universe. They could even be the seeds of supermassive black holes, since after they burn out, their cores could collapse into huge black holes in a single stroke. That would help explain why Webb is finding enormous black holes in the centers of surprisingly young galaxies. Dark stars remain unproven. They may never be confirmed, yet they highlight a crucial point. The hidden particle makeup of dark matter might do more than shape galaxies gently from the outside. It might, in extreme conditions, drive the brightest objects in the universe. Dark matter, quiet across so much of the sky, might become fireworks under the right pressure, and some of its fireworks might never ignite visible matter at all, leaving only invisible shells in their place. The universe is dotted with halos that never grew galaxies. Every dark matter halo in the standard picture is supposed to collect gas. The gas should cool, condense, and eventually ignite into stars. That is how galaxies are made. Halo, gas, ignition. The recipe has been drawn in textbooks for decades. Webb has helped confirm what earlier instruments only hinted at. Some halos skipped the last step. They caught dark matter. They even caught some gas, but they never lit up. No star formation. No visible galaxy. Just a silent, invisible lump drifting through space. These are the failed galaxies. Halos without visible partners. Webb has spotted several in gravitational lensing surveys. Small but significant gravitational effects appear around regions where no galaxy is visible at any wavelength. The infrared pictures show nothing there. The lensing math insists that mass is present. A few of the strongest candidates cluster around bigger galaxy groups. They lurk on the outskirts, contributing small distortions to the lensing map but showing no sign of a host galaxy at their centers. Each one could contain as much mass as a small dwarf galaxy, yet hold fewer than a handful of stars, if any. Why would a halo fail to grow a galaxy? The leading explanation is about feedback. In the early universe, bursts of ultraviolet radiation from the first generation of stars swept through intergalactic space. This radiation, sometimes called cosmic reionization, heated up gas everywhere. In small halos that had not yet cooled enough to form stars, the reionization pushed the gas out of the halo or made it too hot to condense. The halo stayed put, but its gas was either stripped or kept too warm to turn into stars. Other halos may have lost their gas in different ways. A close encounter with a larger galaxy could have pulled the gas away. Supernova explosions inside the tiniest halos could have blown their own gas out into space. Some halos may simply have sat in gas-poor regions of the universe, never gathering enough raw material in the first place. Whatever the cause, the end result is the same. A small, invisible mass wandering through space, forever dark. To picture this, imagine a small town without people. The streets are paved, the houses are built, the lampposts stand, but no one moved in. From a distance, the town looks empty and normal. Up close, you realize that the infrastructure is there, just without residents. That is what a failed galaxy is, cosmically speaking. The scaffolding is in place. The lights never came on. Some theorists think there may be tens or even hundreds of thousands of failed galaxies in the nearby universe. Most are too small to detect with any current telescope. Webb can catch only the largest and closest ones, where their gravitational effect on background light is strong enough to measure. Failed galaxies matter for more than just inventory. They are a direct test of dark matter theory. Different models predict different numbers of failed systems. Cold dark matter predicts many. Warm dark matter predicts far fewer. Fuzzy dark matter, with its wave-like behavior, predicts a sharp cutoff below a certain size. Webb is slowly counting them up. The preliminary counts are hard to pin down, but the evidence that some exist is strong and growing. That is already enough to rule out some extreme versions of warm and fuzzy models. It is the opposite of a non-result. A handful of unlit halos reveals real constraints on the hidden particles, and in the debris of cosmic collisions, Webb is seeing these invisible patterns stretched out like smoke trails. When large clusters collide, the aftermath spreads across space. The most violent cosmic collisions leave trails, rings, and wakes in their wake. The bullet cluster, discussed earlier, was the first clear example. Webb has since imaged several other colliding systems in even greater detail, revealing new kinds of features that look remarkably like cosmic contrails. In some of these systems, dark matter appears to leave behind diffuse trails following its main concentrations. Like smoke behind a bullet fired through a cloud, the invisible mass does not stay tightly packed. A fraction of it smears along the direction of motion, marking the path of the collision. Webb's maps of cluster Abel 520, for example, show a strange, lumpy dark matter distribution with an unusual mass concentration in the core. Where you would expect a smoother pattern after a merger, the data shows a central clump of dark matter that seems slightly offset from its galaxies, combined with an irregular distribution that suggests complex merger dynamics. Even odder features show up in a separate cluster called MaxJ0025, 4 to 1222. Webb re-observations of this object, originally imaged by Hubble, have confirmed and refined a double bullet-like pattern, with dark matter clumps on each side, tracking their host galaxies. The sharper infrared view reveals subtle trails of mass stretching between the two bullets, as if a small amount of dark matter is being left behind in the middle, not quite keeping up with either flying halo. These trails are still a modest fraction of the total dark matter. Most of the invisible stuff passes through cleanly, as expected, but the trails, small and faint, suggest that dark matter is not completely slipping through collisions without leaving a trace. Some of it interacts enough, somehow, to leave behind a wake. That is a big deal. If cold dark matter truly had zero self-interaction, there should be no trails at all. Every collision should leave two clean halos flying apart, with no middle mess. The fact that some middle mess exists, visible only through lensing, hints again at a faint hidden interaction, a little bit of cosmic stickiness among the particles themselves. Picture a swarm of fireflies flying through a field at night. The swarm passes another swarm, and most fireflies zip through unaffected, continuing on their way. But a small number collide, get tangled, or slow down, forming a thin cloud of stragglers in the middle of the crossing. The main swarms continue, but the middle cloud marks where they met. Webb's collision rings and trails feel similar. Two invisible swarms of dark matter cross through each other. Most of the mass continues onward. A small portion hangs behind. The result is a dim, delicate trail between the main clumps. The precise amount of trail-forming dark matter is still being measured. Estimates vary from study to study. What is agreed upon is that it is small, very small, but not zero. And in physics, not zero is a door. These collision trails, along with the drifting halos, the lopsided clusters, the ringed galaxies, and the offsets around individual galaxies, are all forming a quiet chorus. Each one is whispering that dark matter may have properties beyond the original cold particle story. It might interact with itself weakly. It might flow like a fluid in places. It might carry a shadow physics parallel to our own. None of this settles what dark matter is, exactly. It just opens the possibility that dark matter is not one simple thing. It might be a whole hidden family. For most of the 20th century, the hunt for dark matter focused on a single candidate. The standard story assumed dark matter was made of one kind of particle. The most popular guess was something called a weakly interacting massive particle, or WIMP for short. WIMPs were assumed to be heavy, sluggish, and nearly invisible to ordinary matter. Entire underground laboratories were built to search for them, deep inside mountains, shielded from cosmic noise. Years of searching have turned up almost nothing. WIMPs, if they exist, are harder to detect than anyone hoped. Meanwhile, astronomical data has grown more complicated. The cold, simple, WIMP-based picture no longer fits all the new measurements cleanly. Webb's observations have helped push a different idea into the spotlight. Maybe dark matter is not one thing. Maybe it is many. In this alternative picture, the dark sector of the universe is as rich as the visible one. Instead of a single dark matter particle, there could be several different kinds, some heavier, some lighter, some interacting gently with each other, some not at all, some behaving like cold dust, some like warm gas, some like quantum waves. Each component would contribute differently to galaxies, halos, and the cosmic web. Several threads of Webb's data support this multi-component view. The flat cores of dwarf galaxies suggest some kind of wave-like or self-interacting dark matter at small scales. The drifting halos and collision trails suggest a small self-interaction at larger scales. The unusually massive early halos suggest that dark matter may have gathered more aggressively than expected during certain epochs. The unexpected clumping patterns suggest subtle internal structure. No single dark matter model can reproduce all these features at once. Multi-component models, with a cold majority plus a small, warm or interacting minority, can fit a wider range of observations. They are more flexible, though also more speculative. If this is the case, our picture of the universe changes. Instead of one invisible ingredient, there would be many. The dark sector would have its own zoo of particles, possibly its own forces, possibly its own small pieces of internal structure. It would be a parallel branch of physics, connected to the visible world only through gravity, but full of complexity on its own. Imagine a big aquarium with two kinds of fish, goldfish and koi. For years you thought you only had goldfish. You kept searching for tiny goldfish patterns and got confused by some unusual swimming. Then you realize there are also koi, moving differently, bigger, behaving according to their own rules. Once you accept both, the patterns in the aquarium start to make sense. Some fish dart in small swirls, some drift in long paths, each reacting according to their kind. Dark matter might be like that aquarium. Multiple species, each shaping structure in its own way. This view is not a consensus. Many astronomers still prefer single particle solutions, perhaps tweaked to explain the odd data. Others feel that we are approaching a shift in thinking, where dark matter will be understood as a collective of invisible species rather than a lone player. One thing is clear. Webb has not simplified the dark matter problem. It has enriched it. The more the telescope looks, the more variety it finds. Voids with hints of hidden mass, halos with rings, dwarfs with wave-like cores, clusters with drift, filaments with kinks. Each of these could be an accident of complex history, or each could be a clue pointing toward a richer, dark sector. Cold dark matter, once king, is being forced to share its throne. Cold dark matter was the dominant model of cosmology for over 40 years. It underpinned the calculations that described the cosmic microwave background. It fed simulations that produced galaxies matching the real sky at the largest scales. It anchored the standard theory of structure formation. For many decades, the phrase cold dark matter was almost synonymous with dark matter itself. Webb has not destroyed cold dark matter, not yet, but it has shrunk its comfort zone considerably. The old model is now stretched across multiple fronts. Early galaxies are too massive and too mature for its predicted timeline. Small halos are either too abundant or too rare in different analyses. Dwarf galaxies have cores where cold, dark matter expected cusps. Cluster collisions show faint drift and trail effects that a purely frictionless particle should not produce. Ultra-diffuse galaxies and failed galaxies appear in numbers that the simple simulations did not anticipate. Each of these issues, individually, can be patched by adjusting the cold, dark matter picture. Maybe star formation was extreme in the early universe. Maybe feedback from supernovae flattened dwarf cores. Maybe small systematic errors in mass measurements explain some drifts. Maybe simulations missed some subtle cluster dynamics. Each fix is possible. Each fix is also, in some ways, ad hoc. The cost of piling too many fixes on the same model is that the theory loses elegance and predictive power. A model that needs many special adjustments to match observations is not a clean theory anymore. Many astronomers are uneasy with how much patching cold dark matter is now requiring. Webb has also provided direct evidence that other dark matter flavors, like self-interacting dark matter or fuzzy dark matter, fit certain patterns more naturally. They solve several problems at once with fewer tweaks. The cost is that they come with their own troubles at other scales. No alternative fits everything either, but the alternatives are suddenly competitive. The debate in cosmology has shifted in subtle ways. Conference talks that once assumed cold dark matter as the background now explicitly note possible extensions. Papers that once treated alternatives as fringe now list them alongside cold dark matter as candidates worth considering. Graduate students who would have been trained solely in standard cosmology now learn about multi-component dark sectors and modified gravity. To give a concrete sense of the shift, imagine a courtroom where a single suspect has been blamed for a long list of crimes. For years, the evidence seemed to fit, even if a few details were a little off. Then new evidence keeps coming in that does not quite match the suspect's profile. A hair sample does not fit, a fingerprint does not match. An alibi holds up in one case. The judge does not dismiss the suspect, but suspicion starts to fall on a possible group of accomplices. The story gets more complicated. Cold, dark matter is like that suspect, still under serious consideration, still behind many of the crimes, but no longer the sole candidate for explaining every cosmic mystery. Webb has provided most of the new evidence that weakens the single suspect case. Cosmology is in a transitional period. The field is alert, active, and a little unsettled. The next generation of telescopes, alongside more Webb observations, will either confirm one alternative model, point toward a combination, or surprise us with yet another idea. What is no longer likely is that we will go back to the simple, clean story. Some of the most radical alternatives to cold, dark matter are starting to rise as Webb pushes the old guard. Modified gravity, fuzzy dark matter, dark photons, and more. For decades, alternatives to cold dark matter lived on the margins of mainstream physics. They were studied by small teams, published in niche journals, and politely ignored at most major conferences. The reason was simple. Cold, dark matter fit enough of the big picture that alternatives felt like unnecessary complications. Now, thanks in part to Webb, several of these alternatives are moving closer to center stage. Modified gravity is one, originally proposed by physicist Mordechai Milgrom in the early 1980s. This idea suggests that Newton's law of gravity needs a small adjustment at very low accelerations, like those experienced by stars at the outer edges of galaxies. Under this modification, the flat rotation curves of galaxies can be explained without any dark matter at all. The theory predicts particular patterns in galaxy dynamics, and some of those patterns match observations remarkably well. Webb's new rotation curve data, pushed to greater distances than ever, has given modified gravity advocates fresh material to test their ideas. Some results fit the theory surprisingly well, others do not. The theory still struggles to explain some cluster-scale observations, like the bullet cluster, where gravitational lensing requires unseen mass separated from visible matter. But on galaxy scales, modified gravity has become a more serious contender than it was a decade ago. Fuzzy dark matter is another. Proposed as a solution to the dwarf galaxy problems, fuzzy dark matter imagines ultralight particles with quantum wave-like properties on galactic scales. It would produce flat cores in dwarfs, large-scale rings in some halos, and characteristic ripples in structure. Webb's observations of dwarf galaxy cores, ringed halos, and small-scale structure are consistent with certain fuzzy dark matter predictions. At larger scales, fuzzy dark matter struggles, but in the small structures where cold dark matter has trouble, fuzzy models breathe more easily. Dark photons are another idea. In these theories, dark matter particles interact among themselves through a hidden kind of light, mirroring the role of photons in the visible world. Dark photons would carry a new force, invisible to ordinary matter but felt among dark matter particles. Such a force could produce the tiny self-interaction hints Webb is seeing in cluster collisions. It could also support a parallel dark sector with richer internal structure. Dark photon models are being refined to fit various observations. Self-interacting dark matter, more generally, has gained new attention. Models that allow dark matter particles to scatter gently off each other have been proposed since the early 2000s. The predictions include cored dwarfs, slightly lagging halos, and halos that smooth themselves out after collisions. Webb's gallery of drifting, lagging, and smoothed-out dark matter features gives these models a strong, although not conclusive, boost. Axions are another contender. Originally proposed to solve certain problems in particle physics, axions are ultra-light particles that would behave similarly to fuzzy dark matter on cosmic scales. They have their own set of expected signatures, and searches are ongoing in laboratories worldwide. Webb's astrophysical data, combined with direct detection experiments, helps narrow the range of axion properties that are allowed. Each of these alternatives has strengths and weaknesses. Each fits some parts of the data and not others. None is a complete replacement for cold dark matter, at least not yet. But together, they form a growing chorus of possibilities that are now taken seriously. To picture the state of the field, imagine a council meeting where one advisor used to do all the talking. Now, half a dozen advisors sit at the table. Each has a different perspective, different evidence, different weak points. The meeting is noisier. It is also richer. Modern cosmology has opened itself to a crowded council of ideas about dark matter. Webb is the instrument pulling many of those ideas onto the table. And if one of them turns out to be fully right, some cherished concepts may need to be discarded entirely. Imagine, for a moment, that there is no dark matter, no invisible particles, no hidden sea of stuff filling galaxies, no unseen halos or web of cosmic skeleton, only the normal matter you see, and a different, deeper law of gravity that we have not yet fully understood. What would that mean? A small but persistent group of physicists think this is still a possibility. If dark matter does not exist as a substance, then everything we have been mapping, from galaxy rotation curves to cluster lensing, must be explained by changes in the laws of gravity at cosmic scales. That would be a revolution comparable to Einstein's overthrow of Newtonian physics a century ago. It would force a rewrite of astronomy, cosmology, and parts of particle physics. The case for a no dark matter scenario rests on several threads. Decades of direct searches have failed to find dark matter particles. Theories of modified gravity, especially on galaxy scales, match certain observations with surprising accuracy. Some patterns in Webb's data, like certain rotation curve shapes and galaxy dynamics, fit modified gravity predictions better than simple cold dark matter. The case against is also strong. Cluster collisions like the bullet cluster are notoriously difficult to explain without invisible mass separated from visible matter. Gravitational lensing on cluster scales requires mass distributions that modified gravity has not cleanly matched. The cosmic microwave background fits cold dark matter predictions quite well, in a way that most modified gravity theories have struggled to reproduce so far. If modified gravity, or some successor to it, turned out to be correct, many cherished concepts would dissolve. The cosmic web would become a web of modified gravity flows rather than dark matter filaments. Galaxies would float on fields of enhanced gravity instead of in halos of invisible particles. Dwarf galaxies would keep their shapes through stronger than expected gravitational pull, not through massive invisible cocoons. Webb's data, so far, is not decisive on this question. Some of its findings make cold dark matter harder to maintain. Others do the same for pure modified gravity. The most likely outcome, many physicists say, is that the real story involves some form of invisible matter, although perhaps not the particle we have been searching for. Modified gravity might still play a smaller role, or the truth might be a combination never fully imagined. If dark matter were fully disproved, the consequences would go beyond astronomy. Particle physics, cosmology, and the philosophy of science would all be affected. Entire generations of theories and experiments would have to be reorganized. Labs built deep under mountains to catch WIMPs would have to retool for other physics. Simulations run on supercomputers for decades would need to be redone from scratch. To picture how big this shift would be, imagine opening a familiar map of your city and discovering that many of the streets you thought you knew were never really there. You always got from one place to another, so the map felt right. But now you realize the roads are different, and the way the city is organized is different from what every book said. You can still drive, eat, and live, but your mental model of the city has changed profoundly. That is close to what would happen if dark matter were fully wrong. The universe would still work. You would still see the same stars. But the way everything was connected, organized, and held together would need to be redrawn. Most astronomers do not expect this complete overthrow. Most expect a modification, not a revolution. But the fact that the possibility is taken seriously at all says how much Webb has stirred up the old certainties. And Webb is not done stirring. Its next dark matter targets are already being selected. The telescope keeps working, and the proposals keep coming. Every year, astronomers from around the world submit observing plans for Webb. Many of those plans focus on dark matter. Some aim at huge survey programs, mapping clusters across wide stretches of the sky. Some target individual systems that have already shown strange properties. Some aim at the earliest galaxies, trying to pin down exactly when halos became too big for standard models. A few are specifically aimed at a single object that has already become something of a legend. This is a cluster known by a long catalogue name, usually shortened to the problem cluster in informal talks. It lies several billion light-years away and has been studied by multiple telescopes before Webb. Hubble noticed that it had an unusual mass distribution. X-ray telescopes saw that its gas was in a complex state, possibly from a recent merger. Ground-based lensing suggested a dark matter map that was lumpy in unexpected ways. Webb's early observations of this cluster confirmed the trouble. The dark matter appears in at least 3 major clumps, none of them cleanly aligned with the brightest galaxies. One clump sits in a region with hardly any galaxies at all. Another clump is strung out in a long, thin shape that looks unlike any cluster feature in the standard simulations. The third clump is where you would expect it, near the main group of bright galaxies, but it is smaller than predicted. Several theories have been floated. Maybe this cluster is the aftermath of a 3-body merger, where 3 smaller clusters collided in close succession, leaving a complicated mass distribution. Maybe it is a cluster caught at a rare moment in its evolution. Maybe it represents a structure that the standard model cannot produce at all, and would require new physics to explain. The next round of Webb observations will push further. Deeper imaging, more detailed lensing, and spectroscopy of dozens of background galaxies will give a much finer picture of the mass distribution. If the strange features are real, Webb will confirm them with higher confidence. If they are artifacts of earlier analysis, they will vanish. Either result is informative. Beyond this one cluster, Webb's next dark matter targets are broad and ambitious. Large programs are planned to map the dark matter web across huge patches of sky. Other programs will focus on the distant early universe, attempting to catch the earliest halos at the moment they begin to form. Still others will zoom in on dwarf galaxies closer to home, refining the measurements of their cores and orbits. Future telescopes, such as the Nancy Grace Roman Space Telescope, the Euclid mission, and upcoming ground-based giants, will work alongside Webb. Each will add a different kind of data. Some will cover wider fields. Some will see deeper into certain wavelengths. Together, they will form a combined assault on the dark matter problem. The pace of discovery is picking up. In a few years, the field may look very different from today. Webb has already handed astronomers a puzzle they are still trying to solve. The next years will determine whether the strange features continue to stack up, or whether they start to fit into a new, coherent framework. Whatever the outcome, the universe is about to be mapped in far greater detail than anyone imagined a decade ago, and the picture that is emerging, bit by bit, is strange in ways that go far beyond dark matter alone. Webb is revealing a universe that is larger, emptier, weirder, and more alive, with hidden structure, than the old cosmology suggested. Stand back and look at the sky as Webb now sees it. The universe is stranger than the one we thought we knew. A huge fraction of its mass is invisible, and that invisible mass does not stay neatly tucked around galaxies. It drifts, it tilts, it leaves trails, it skips galaxies, it piles up in empty voids and thins out in places where it should be thick. It forms shells, bridges, and cocoons that do not match the old diagrams. The universe is also emptier than we thought. Voids are bigger, quieter, and more strangely structured than older surveys suggested. Filaments between clusters have gaps, kinks, and shifting thicknesses. Dark matter does not fill space smoothly. It weaves, skips, and bunches in patterns that hint at internal rules we have not yet cracked. And the universe is more alive than we thought. Alive in the sense of moving, changing, responding. Collisions between clusters are not quiet pileups. They are events where different kinds of matter separate, leaving trails of dark mass drifting through empty space. Galaxies are not static structures. Their halos tilt, wobble, and reshape in response to hidden forces. Even the smallest systems have their own histories, their own flows of gas, their own secret physics. Webb has not given us a final answer about dark matter. In many ways, it has done the opposite. It has replaced one big question with many smaller, sharper questions. What are the rings around some halos? Why are some galaxies lopsided? Why do some dwarfs have cores instead of cusps? Why are some early galaxies impossibly mature? Why do some clusters show drift and trails in their dark matter? Each of these questions is a handle. Each handle, once pulled, may reveal another layer of physics underneath. The universe that is coming into focus is more like a living ecosystem than a static diagram. Dark matter behaves in ways that depend on context. In dwarfs, it seems softer and more wave-like. In clusters, it can lag and drift. In voids, it lingers in amounts unexpected. In ancient galaxies, it forms with a speed that defies old timelines. The picture is complex. It is also beautiful. For human observers, the implications are profound. Most of what exists in the universe remains invisible to our eyes. Even with our best tools, we see only the glittering foam on top of a dark ocean. Yet that foam, lit by stars and galaxies, provides clues about the ocean beneath. Every twist of starlight, every warped galaxy image, every subtle motion of ancient starfields carries a whisper about the hidden deep. Webb has been listening carefully to those whispers. Its data is teaching us that the cosmos is more surprising than any textbook prepared us for. Galaxies without halos, halos without galaxies, stars possibly powered by dark matter, rings, trails, bridges, kinks, and shells made of invisible stuff. None of this reduces the importance of cold, quiet curiosity. The basic reality is simple. We do not fully understand what fills most of the universe. We only know that it shapes everything we see. Without it, galaxies would dissolve, stars would scatter, our own Milky Way would not exist. With it, we live inside a cathedral of invisible architecture. Webb has given us the first detailed sketch of that cathedral's walls. The sketch is rough in places. The sketch is wrong in others, but it is richer, stranger, and more alive than any previous map of the heavens. The work is just beginning. Webb keeps watching. The sky keeps whispering. And somewhere out there, in a patch of space we have not yet imaged, the next impossible discovery is already sitting, waiting to be found.